Before we talk about magnetars, we need to start somewhere simpler. We need to talk about stars. A star is basically a giant ball of gas, mostly hydrogen. And it's been doing the same job for billions of years. That job is this: squeezing hydrogen atoms together so hard that they merge. That process is called nuclear fusion. When atoms fuse, they release energy. That energy pushes outward. It's like an explosion that never stops. But here's the important part. The star's own gravity is pulling everything inward at the same time. So a star is a tug of war. Gravity pulling in. Fusion pushing out. And for most of a star's life, these two forces are perfectly balanced. This balance is called hydrostatic equilibrium. Big name, simple idea. Push in equals push out. Our Sun has been in this balance for about 5 billion years. It will stay balanced for about 5 billion more. But not all stars are like our Sun. Some stars are much, much bigger. We're talking 10, 20, even 50 times the mass of the Sun. These massive stars burn hotter, brighter, and much faster. They go through their fuel in just a few million years, not billions. And when they run out of fuel, something truly extraordinary happens. But we'll get there. First, let's understand what happens when that balance breaks. Think of it like this. The fusion fire in the core is what holds the star up. Take away the fire, the gravity wins instantly. So everything depends on that fuel. As long as hydrogen is available, the star lives. When it's gone, the clock runs out. For the biggest stars, that fuel runs out in spectacular fashion. And what comes next changes everything. Let's look at how a massive star dies. When a massive star runs out of hydrogen, it doesn't just stop. It tries to keep going by burning something else. First it fuses helium, then carbon, then oxygen, neon, silicon. It keeps going, working through heavier and heavier elements. Each step releases less energy than the one before. The star is buying time, but each fuel lasts a shorter and shorter period. Then it reaches iron. And iron is the end of the road. You cannot get energy from fusing iron. It actually costs energy. So when the core becomes iron, fusion stops completely. The outward push disappears in an instant. Without that outward push, the core collapses. Not slowly. This collapse happens in less than 1 second. The outer layers of the star come crashing inward at roughly a quarter of the speed of light. The numbers here are almost impossible to imagine. Then those infalling layers hit the ultra-dense core and they bounce. A massive shockwave blasts outward. This explosion is called a core collapse supernova. For a few days, this single exploding star can outshine an entire galaxy of 100 billion stars. The outer layers are blasted into space. They will form beautiful clouds of gas and dust called nebulae. New stars will eventually form from those remains. But the core, the collapsed iron core, that's the part we care about for this story. What happens to it? If the original star was big enough, but not too big, the core survives the explosion. It becomes something called a neutron star. If the star was truly enormous, say more than 25 solar masses, the core collapses all the way into a black hole instead. Today we are focused on the neutron star path. Because inside that category, there is something even more extreme waiting for us. But first, let's understand what a neutron star actually is. Because until you understand that, magnetars won't make any sense. A neutron star is what remains when the core of a massive star collapses. And it is, without any exaggeration, the densest object you can touch in the universe. Let's talk size first. A neutron star is roughly 20 kilometers across. That's about the size of a city. But this city-sized object contains more mass than our entire Sun. Our Sun is 1.5 million kilometers wide. That mass, squeezed into 20 kilometers. How dense is that? 1 teaspoon of neutron star material would weigh about 1 billion tons on Earth. 1 billion tons in 1 teaspoon. To understand why it's so dense, we need to talk about what happens to atoms during the collapse. Normally, an atom is mostly empty space. The nucleus is tiny, and the electrons orbit far away. If the nucleus were a marble, the electrons would orbit a kilometer away. During the collapse, the pressure is so extreme that it forces electrons into the nucleus itself. Electrons and protons combine to form neutrons. The empty space inside atoms is eliminated. Almost entirely. What you're left with is a ball of pure neutrons packed tightly together. This is called neutron degeneracy pressure. The neutrons themselves resist being squashed any further. It's what stops the collapse from continuing into a black hole. So a neutron star is this: a ball of pure neutrons, city-sized, with more mass than the Sun, and spinning incredibly fast. How fast? Some neutron stars spin hundreds of times per second. If Earth spun that fast, the surface would be moving faster than a speeding bullet. And neutron stars have strong magnetic fields. Every object that spins and has charged particles inside it generates a magnetic field. The neutron star does this extremely well. For a typical neutron star, the magnetic field is already about 1 trillion times stronger than Earth's. 1 trillion times. That already sounds impossible. But a magnetar does not have a typical neutron star magnetic field. A magnetar's magnetic field is another 1,000 to 10,000 times stronger than that. We are now standing at the edge of the most magnetic objects ever discovered. Let's step over that edge. Before we go further, let's make sure we understand magnetic fields. Because magnetars are defined entirely by their magnetic field. It's the whole story. A magnetic field is a region of space where magnetic force acts. You can't see it. But it is absolutely real, and it can push and pull on certain materials. Here on Earth, the magnetic field is generated by liquid iron moving in our planet's outer core. That moving charged material creates electric currents, and those currents make the field. The strength of a magnetic field is measured in a unit called Tesla. Earth's field is about 50 microtesla. A fridge magnet is around 10 millitesla. The strongest magnets humans have ever built in a lab reach about 45 Tesla. That's already powerful enough to levitate a frog, and yes, scientists have actually done that. A typical neutron star sits at around 10 to the power of 8 Tesla. That's 100 million Tesla. Way off our scale. And a magnetar. A magnetar reaches 10 to the power of 11 Tesla. 100 billion Tesla. This is the strongest magnetic field known to exist anywhere in the universe. At this strength, the magnetic field is so powerful it affects the very structure of atoms. Electrons are forced into completely different shapes. Atoms near a magnetar become long and thin, like needles, stretched along the magnetic field lines. This is called magnetic distortion of the vacuum itself. This is not science fiction. At magnetar field strengths, even light behaves differently. The field is so intense it changes how photons travel through space. This effect is called vacuum birefringence. The magnetic field is so strong it splits light into two components that travel at slightly different speeds. We've actually observed evidence of this effect around a neutron star called RxJ 1856. It's one of the strangest confirmations of a physics prediction ever made. So before we even get to what magnetars do, we already know their magnetic fields are strong enough to reshape atoms and bend light. That should give you a sense of what we're dealing with. Now the big question. How does a neutron star develop a field this extreme? What makes a magnetar different from an ordinary neutron star? The answer comes down to what happens in the first second after the supernova. Everything depends on that 1 second. When the core of a massive star collapses, it happens so fast that angular momentum is conserved. This is the same physics that makes a figure skater spin faster when they pull in their arms. The original stellar core was huge. When it collapses to a 20-kilometer ball, the rotation speeds up enormously. Conservation of angular momentum guarantees it. Now here's where magnetars diverge from regular neutron stars. Scientists believe a magnetar forms when the newly born neutron star spins exceptionally fast enough to create a dynamo. A dynamo is a process where spinning conducting material amplifies a magnetic field. Your car's alternator is a dynamo. Earth's outer core is a dynamo. A young neutron star can also become one. In the first second or two after birth, the neutron star is extremely hot. The material inside is still fluid. It churns and convects. These convection currents, combined with rapid rotation, amplify the magnetic field exponentially. This process is called the magnetorotational instability. Within just 1 or 2 seconds, the field reaches those extraordinary magnetar level strengths. But here's the trade-off. Building that field requires energy. It drains rotational energy. So magnetars actually slow down faster than regular neutron stars. In about 10,000 years, a magnetar slows down dramatically. The field also slowly weakens over time. Eventually, millions of years later, it may become a relatively quiet neutron star. So magnetars are relatively young objects. Most of the ones we've found are only a few thousand years old. They are literally teenagers in cosmic terms. We've detected about 30 magnetars in our galaxy so far. Given how short-lived they are, there are likely many more we haven't spotted yet. So we know how they form. We know how strong they are. Now let's talk about what they actually look like, starting with their surface. A magnetar has a rigid crust, made of crystalline neutron-rich nuclei. And that crust is under unimaginable stress from the magnetic field pressing and twisting against it. Think of the magnetic field like a twisted rubber band, wrapped tightly around the star. It stores enormous amounts of energy. And sometimes, that energy has to go somewhere. When it does, the crust cracks. And that crack is nothing like anything we have here on Earth. Let's look at that next. You've heard of earthquakes. A rupture in Earth's crust releases stored energy. Tectonic plates slip, and energy radiates outward as seismic waves. A starquake is the same basic concept. The magnetar's crust cracks, but the energies involved make the most powerful earthquake on Earth look like a tap on the shoulder. Let me put that comparison in perspective. One of the largest earthquakes ever recorded was the 1960 Valdivia earthquake. It released about 10 to the power of 18 joules of energy. A magnetar starquake can release 10 to the power of 46 joules. That is 100 trillion times more energy. The bar for the earthquake is invisible at this scale. The crust of a magnetar is incredibly hard, the strongest material known in nature. It can withstand enormous stress. But eventually, the magnetic field wins. When the crust shifts by just a fraction of a centimeter, not even a full centimeter, the stored magnetic energy is released all at once. The surface of the magnetar moves less than a centimeter, but the energy released in that fraction of a second is more than the sun releases in 100,000 years. This energy erupts as a massive burst of X-rays and gamma rays. These are the most energetic forms of light. They travel at the speed of light in all directions. This event is called a magnetar burst. They are detected regularly by X-ray observatories. Most magnetars produce many small bursts over years and decades. But occasionally, something much larger happens. Instead of a small crack, a huge section of the crust ruptures at once. This produces what scientists call a giant flare. A giant flare is a different category of event entirely. 3 have been observed close enough to study in detail. Each one was astonishing. The 2004 giant flare from SGR 1806-20 was detected on December 27. In just 0.2 of a second, it released more energy than the sun produces in 250,000 years. That flare was so powerful it affected Earth's ionosphere from 50,000 light-years away. Even at that incredible distance, it partially ionized our upper atmosphere. The ionosphere disturbance caused detectable changes in low-frequency radio communications. Scientists actually measured it from 50,000 light-years away. Now, that flare was at 50,000 light-years. If something like that happened close to us, say a few light-years away, the situation would be very different. We'll get to that soon. But first, let's understand how these bursts work in detail. Let's go back to 1967. A young PhD student named Jocelyn Bell was working at Cambridge University, analyzing radio telescope data. Her telescope was looking for something completely different, quasars. But something unexpected appeared in the data. A strange, repeating signal. The signal repeated every 1.33 seconds. Exactly. Not approximately, exactly. No natural process they knew of could do that. Jocelyn and her supervisor Anthony Hewish considered and rejected the alien hypothesis. The signal was too perfect, too regular, but also too simple. After months of investigation, the team concluded, this must be a rotating neutron star. A new kind of astronomical object. They named it a pulsar, short for pulsating radio star. Anthony Hewish later won the Nobel Prize in Physics for this discovery in 1974. Jocelyn Bell, who actually found it, was not included, a decision still controversial today. Now let's do something that science communicators love to do. Let's ask a completely hypothetical but very instructive question. What would a magnetar actually do to Earth? First, some good news. There are no magnetars near Earth. The closest known magnetar is about 9,000 light-years away. We are completely safe. The 2004 giant flare already showed us what happens at 50,000 light-years. It disturbed our ionosphere. So let's scale this thought experiment by distance. What happens as we bring it closer? At 50,000 light-years, what actually happened? We got ionospheric disruption. Some radio communication interference. Detectable, but not dangerous. At 10,000 light-years, a similar flare would be significantly more intense. The ionospheric disruption would be much stronger. GPS and some satellite systems might be affected temporarily. At 1,000 light-years, we'd be in serious territory. The gamma radiation from a giant flare at this distance could begin to deplete the ozone layer. Significantly. The ozone layer protects us from ultraviolet radiation from the sun, damage it, and UV levels at the surface spike. This affects ecosystems, agriculture, and human health on a global scale. Interestingly, some scientists have proposed that mass extinction events in Earth's history may have been triggered by nearby gamma-ray events, possibly including magnetar flares. At around 100 light-years, the gamma radiation would be severe enough to cause major ozone depletion globally. Life on Earth's surface would face a UV catastrophe. At 10 light-years, just 2.5 times the distance to our nearest star, Proxima Centauri, even a modest burst could deliver a lethal dose of gamma radiation directly. At 1 light-year, we simply do not survive as a civilization. The magnetic field of the magnetar alone would be powerful enough to affect physical processes on Earth from that distance. And if, in our wildest thought experiment, a magnetar were placed just 1 astronomical unit from Earth. That's the distance from the Earth to the Sun. The planet would simply cease to exist. The magnetic field at that range would be roughly 10 billion times stronger than anything that could exist naturally near Earth. Atoms would be stripped apart. Matter itself would be reorganized. Now, none of this is going to happen. There are no magnetars anywhere near us. But this thought experiment tells us something important about just how extreme these objects are. The scale of energy a magnetar can release, the kind that reaches us faintly from 50,000 light-years, represents physics operating at its absolute limits. Magnetars are invisible to the naked eye. Not because they're faint, they are incredibly bright in X-rays and gamma rays. But our eyes can't see those wavelengths. Earth's atmosphere, fortunately, blocks X-rays and gamma rays from space. That's good for us, but it means that to detect magnetars, we need telescopes in space. The key observatories for magnetar science are space-based X-ray and gamma-ray telescopes. Some of the most important are the Fermi Gamma Ray Space Telescope and the XMM Newton X-ray Observatory. When a magnetar bursts, it emits a sharp spike of X-ray and gamma radiation. Space telescopes detect this spike, record its arrival time and spectrum, and alert astronomers. From the timing of the pulses, we can determine the spin rate of the magnetar. From how the spin rate is changing over time, we can infer the magnetic field strength. This is called the spin-down method. The magnetic field acts like a brake on the spinning star. A stronger field equals faster spin down. So measuring the spin-down rate tells you the field. The energy of the X-ray photons also tells us about the magnetic field. Near a magnetar, photons get their energies shifted by the intense field. This creates a distinctive spectral signature. We also detect magnetars in quiescence, between bursts. In their quiet state, they still glow steadily in X-rays, powered by the slow decay of their magnetic field energy. In fact, magnetars were originally discovered as a separate class of objects before scientists fully understood what they were. They were called anomalous X-ray pulsars and soft gamma repeaters. The name soft gamma repeaters comes from the fact that they repeatedly emit bursts of gamma rays that are slightly less energetic, softer, than the most extreme gamma ray events. Today we have catalogued about 30 magnetars, with more candidate objects being studied. The known magnetars are all within our galaxy, the Milky Way. In 2020, an extraordinary event occurred. A magnetar in our galaxy, SGR 1935 plus 2154, emitted a burst that was detected not just in X-rays but also in radio waves. This was the first time a fast radio burst was directly connected to a known magnetar. This single observation told us more about fast radio bursts than a decade of speculation had. It strongly suggested that many of the mysterious FRBs we observe from distant galaxies are also magnetar flares, just much more distant ones. That's the power of a well-timed observation. One lucky catch, and a whole category of cosmic mystery gets at least a partial answer. This is what makes magnetar science so exciting right now. We are actively decoding them. Let's zoom out now, not just to understand what magnetars are, but to understand what they tell us about the universe. Magnetars represent the extreme end of what matter can do. They push every physical force to its limit. Gravity, electromagnetism, the strong nuclear force, all operating at maximum intensity. This makes them natural laboratories. We can observe physics in conditions we could never create here on Earth. Our best particle accelerators can't come close to the conditions inside a magnetar. By studying magnetars, we test our theories of matter under extreme pressure. We test quantum electrodynamics, the theory of how light and matter interact, in the strongest magnetic fields that exist. We also use magnetars to test our understanding of neutron star interiors. What is matter like when it's compressed to nuclear density? Physicists have several competing models, and magnetar observations help us decide between them. One of the big open questions is whether the very core of a neutron star, the absolute center, might contain free quarks. Quarks are the building blocks of protons and neutrons, normally confined inside them. At the densities found in the center of a neutron star, the pressure might be so extreme that protons and neutrons dissolve and their quarks float freely. This would create what's called quark-gluon plasma. We don't know for certain, but by watching how magnetars behave, their spin-down rates, their flare energies, their cooling rates, we collect evidence that helps us discriminate between models. Magnetars also connect to gravitational wave astronomy. When two neutron stars merge, they can produce a merged object that briefly becomes a magnetar before collapsing further. Gravitational wave detectors like LIGO can detect that merger. In 2017, the merger of two neutron stars was detected by LIGO and accompanied by a short gamma-ray burst. This event, called GW 170817, confirmed a direct link between neutron star mergers and some gamma-ray bursts. Future gravitational wave detectors, more sensitive ones being planned right now, will allow us to study post-merger neutron stars and possible transient magnetars formed in those collisions. There's also the question of magnetars in other galaxies. We've only directly confirmed magnetar flares in the Milky Way and the Magellanic Clouds. But fast radio burst detections suggest they exist throughout the observable universe. The universe is full of magnetars we haven't detected yet, most too distant, most quiet at the moment we looked. But every new X-ray or gamma-ray telescope we launch increases our chances of catching one mid-flare. So here is what magnetars really are. They are the universe's extreme experiment, a natural test of physics at its absolute boundary. They were born in stellar catastrophe, they live briefly and violently, and they tell us, from tens of thousands of light years away, things about matter and energy that we simply cannot learn any other way. And that, honestly, is one of the most remarkable things about being alive at a time when we can study them at all.